Hello everyone, welcome back to the latest lecture session. So I believe we have been discussing acids and bases, right? And we also discussed kinetics in relation to acids and bases. And what did we see? We looked at the characteristic times we look at with respect to our systems, and then looked at the usual half times. And I believe the half times we said were around or less than 1 millisecond, let's say, right? And thus we mentioned that the kinetics of these acids and base reactions are pretty fast, and thus what can we infer from this particular information? We see that for most of our systems the kinetics is so fast that we end up reaching equilibrium by the time we look at the sample or such, or we analyze the sample. So we are going to be looking at only equilibrium with respect to our acid and base systems, right? And then we moved on to discussing the relevant aspects. So the first major aspect is going to be the acid dissociation constant. So for example, for HA dissociating into H plus and A minus, it is going to be activity, or here in this case I am going to switch over to concentration by HA, and we introduce the new term to acid dissociation constant Ka, and then pKa equal to minus log Ka. And these are constants for specific acid, right. So we are going to go into that in greater detail, and then we started looking at or derived the Henderson-Hasselbalch equation. And what is that? It gives us the relationship between pH, pKa and the relative concentrations of the deprotonated form and the protonated form. So keep in mind that whenever we talk about equilibrium constants, we need to express them in terms of activities. But if we assume that the activity is relatively equal to concentration, so that is what we have here, and this obviously will work out only in dilute systems, I guess, right. And this is something we already discussed in our equilibrium fundamental classes, right. So we are trying to understand this system better. So in that context, what have we looked at? So we looked at pH equal to pKa. We considered pH is greater than pKa, and we considered pH is less than pKa, and the three cases more or less relate to A minus being equal to HA in concentration, right, and then A minus being greater than HA in concentration, yes, and then obviously A minus being less than HA in concentration. So what does this mean, I guess? And for this particular case, so for any concentration, this obviously is independent of the total concentration of your acid that you have initially, let us say, right. So let us try to jot this down in terms of a graph, and then look at how to interpret the graph, right. So this is something that is important again, or remarkably important. So we have pH and we have concentration here, right, and I want to be able to plot HA and A minus on this graph now, right. And so keep in mind that this is our equation, right. This is the pH of the solution or water, and 0 to 14, let us say, or any other scale, and this is the concentration of your particular species, and the species are HA and A minus. So take a moment and try to think of how the graph is going to be. Would it be linear, right, or what shape would it take now, right, and if they are going to intersect, at which point are they going to intersect, and so on. So first obviously the fundamental aspect is going to be dependent upon pH equal to pKa plus log A minus by HA. So obviously it is always a ratio. So as you see, HA, everything at pH 0 is going to stay as HA. So as you increase the pH, it can dissociate further, and the HA concentration keeps decreasing, right, and that is what you see here. As you keep increasing the pH, right, the HA concentration keeps decreasing, right. I mean, let me try to get a better figure here. Again, the key is that as the pH increases, HA will dissociate, right, H plus and A minus. So, it is an equilibrium, it is a fine balance here that depends upon the pH of the particular system and obviously the pKa, and we are going to look at that, I guess. So, it is going to decrease, 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 an inflection point, let us say, and then again taper out. So, thus let us say is the graph for HA, right. And at the same time, what is going to be the behavior of your the conjugate base now, or A minus, right. So, as HA, or when 1 mole of it dissociates, you are going to have formation of 1 mole of your conjugate base. So, in the same case, we are going to have this particular system. Okay, again pardon my poor drawing skills. So, this is going to be A minus. So, what does this mean? So, as the concentration of HA in your solution is decreasing, the concentration of your A minus is going to increase, right, and obviously there is going to be a point at which both of them are going to be the same, right, and again A minus when as A minus increases, HA concentration decreases, right. So, at the highest pH, what is going to happen, or what do we notice, that everything is going to be, or all the acid is going to be in terms of, or is going to dissociate, right. All the acid that we had initially is going to dissociate, or it is only going to be in the form of A minus, and at lower pH we see that it is going to predominate as HA. So, we just use generic terms, lower pH, higher pH and so on, but we need to look at the reference, right. And what is the reference here? We look at the point of intersection, or where we have equal concentrations, or as we just looked at it earlier, and the case is pH equal to pKa, and at that case we notice that A minus is equal to the concentration of HA. So, this is the inference here, right, pKa. So, let us try to understand this figure now. So, when pH is greater than pKa, right. So, when pH is greater than pKa, so in this particular region, let us say, which form is predominating now? Is it the acid HA or the base, right. So, as you see, the form that is predominating here from this graph, as you see, is the conjugate base, or A minus, or the deprotonated form. So, when pH is greater than pKa, the deprotonated form predominates. But what about it in this particular zone, let us say, when pH is less than pKa. So, what form predominates now? It is going to be the protonated form HA. Or what does that mean now in practical terms? So, let us say if I take a particular acid, let us take the example of acetic acid CH3COOH, right, and I know that its pKa is around 4.7, I believe. So, do not take my word on that, let us go with that particular value for now, right. So, take this example, let us draw a figure and then try to look at that particular case. So, what do we have here? We have pH and we have concentration, and so acetic acid I am going to, what do you say, use the form of HAC, I am going to use that to represent acetic acid. So, that can dissociate into H plus and acetate ion, right. This is what you can have. So, I want to draw this figure here and try to look at the conclusions that we drew in the previous slide, right. So, here I am going to have the generic figure out here. Right, this is HAC, and obviously this is going to be AC minus, or the acetate ion, and this, the value of at which both HAC and AC minus are in equal concentrations, that is going to be the pKa value, and the pKa value, as we just mentioned, was 4.7, I believe, right. So, this is what we have. So, now think of this now, let us say if I want to, or have a solution at pH 7 and I want to, let us say, get to pH 2 for example, right. I need to add an acid, that we are aware of, or I need a source of H plus, that is what it means, right. More or less, if I want to decrease the pH from 7 to 2, I need a source of H plus. So, let us see if the choice of acetic acid, is that a good choice, can I use acetic acid to do so. So what happens to acetic acid as I what do we say, dump it at pH 7, let us say, or add acetic acid to solution at pH 7. So pH 7 is somewhere 4.7, let us say 5.7, 6.7, let us say pH around 7 here, let us say, right, the pH is around 7 here, let us say. So at pH 7 we see that HAC that you add to your solution here at pH 7 will dissociate into H plus and AC minus, or at pH 7 acetate is going to donate the proton, right. But as you keep adding H plus, right, what is going to happen to the pH? The pH is going to decrease. So from here, let us say example, this is pH 7, I am moving to my left now, right. So what does that mean now? As I keep decreasing the pH, the ability of the acetic acid to donate the proton keeps decreasing, and that is what you see here, right. So as you come here, for 1 mole of your HAC, you see that lesser number of moles of protons are going to be given out, right. So that is what you see here at this particular point in space, and this is 4.7 now. So below 4.7, or let us say if I need to go to 2, or let us say at pH 3, and let us say this is pH 3, right, and if it is at pH 3 and I add acetic acid to the particular solution, will it be able to bring down the pH? Not in the usual cases, unless you dump a lot of it, or even if you dump a lot of it, probably not. Why is that? Because any HAC that you add at pH 3, as you see that pH 3 is less than the pKa, right, and what does that mean? It means that HAC would prefer to stay as HAC and will not donate the proton here, right, it will not donate the proton. So the acid is not dissociating, right. So thus you have no more source of H plus, right, and thus the pH will not drop further. So that is what you need to understand here. So again same case here, right. So when the pH is greater than pKa, the acid can dissociate and act as a source of your protons, right. But when pH is less than pKa, what do we see? The predominant form is the protonated form, or you will have a lesser ability of the acid to donate its proton, or lesser ability, as in that is a layman's term, we can calculate that obviously, right. So the number of moles available of proton would be less, and as you move far away to the left from your pKa, it is mostly going to stay as its protonated form and it will not give out its proton, right. So that is what we understand from here. So from here I guess obviously we see that pKa gives us an idea about the strength of the acid. So many people would have mentioned that okay, HCl is a strong acid, H2SO4 is a strong acid, and maybe acetic acid not such a strong acid, and so on. So why is that? If I look at the pKa values, maybe for HCl and so on, I think 0 or such, or equal to 0 or near about 0, right. For acetic acid we see that it was around 4.7 or 4.3, I am not sure. So based on this, you know, what do I know that when the pKa of my particular acid is very low, what does that mean? Let us again draw that for HCl, let us see. So it means that at any pH it is going to dissociate. So this is my HCl, right, and this is the conjugate base which is going to be Cl minus, because the pKa value is very less, almost equal to 0 I believe, right, and this is with respect to your pH, and this is the concentration. So I am drawing HCl here. So compare that with the acetic acid, the pK of the acetic acid was somewhere here 4.7, right, and so here though with respect to HCl you see that in the normal range of pH, because pKa of that particular HCl is always less than, for HCl what do we see, pKa is less than almost all the pH, all pH range I guess, right, it is always less than the pH range that we come across. So HCl will always end up donating its proton, which is not the case with the other acids, especially like acetic acid or arsenic acid and so on, which we looked at. So again pKa will give you an idea about the strength of the acid, and this is what we just discussed. And at pKa we have conjugate acid, and conjugate base at equal concentrations, right. So, let us see what else we can think about, let us say distribution with respect to pKa and so on. So, one aspect I guess I want to quantify is that if pH minus pKa is equal to 1 and pH minus pKa is equal to minus 1. So, let us see what is the scenario or what can we understand from this, let us say. So, we know that pH is equal to pKa plus log deprotonated form by the protonated form, right. This is what we have, yes, pH equal to pKa and so on. But when the first case, if I am considering the first case, pH minus pKa is 1. So, 1 is equal to log A minus by HA, right. So, what does that mean? Concentration or activity of A minus by activity of HA is going to be equal to 10 to the power of 1 or 10. So, when pH is greater than pKa by just 1 unit, so because it is a logarithmic unit I guess, it means that the concentration of A minus is going to be 10 times the concentration of HA, right. So, what does this mean? It means that concentration of A minus is equal to 10 times the concentration of HA, right. So, let us look at another example I guess, right. So, one example we looked at was when pH minus pKa is equal to 1 and we see that the activity of A minus or the concentration is going to be 10 times the activity of HA, right. And when the other aspect pH minus pKa is equal to minus 1, what is it going to be? So, we have pH minus pKa is equal to log activity of A minus by activity of HA. So, minus 1 equal to log activity of A minus by activity of HA. So, what does that mean? It now means that one by 10, right. What does that mean now? So, it means that it is a tenth of the concentration of HA, right. So, what do we understand from this now, right. So, again this is my pH and this is my HA and this is my A minus and this is my pKa and this is the graph, x axis is pH. So, within 1 unit from pKa plus 1, so pKa plus 1 and 1 unit to the left which is pKa minus 1. So, what do we observe? We observe that there is a tenfold increase or decrease in the relevant speciation. So, as in at this particular point, what do we see? We see that the A minus concentration is almost 10 times that of HA. Obviously, the graph is not to scale, that is why you are unable to understand that here I guess. And in the other case, when pKa at pKa minus 1, let us say, we see that A minus is going to be HA by 10. So, more or less the effective region with respect to proton accepting the proton or donating the proton is pKa plus or minus 1. So, that is another take home message for us, right. So, now I believe I have some practical examples. Let us look at them and try to understand those particular aspects in relation to what we see in nature. So, let us say in general people look at ion exchange. This is something we are going to talk about now. Ion exchange, as the process indicates, you have let us say different binding sites, your particular ion here depending on anion or cation I guess, and the resin here, they can be exchanged with the particular anion or cation on this particular binding site, right. So, it is ion exchange process. So, we will see how pH plays a role, we will look at a specific example. So, before going further, here are some of the data, let us look at that. For ammonium, looks like the pKa value is 9.25. For arsenic, because it has the ability to donate 3 protons, we have 3 pKa values, pKa1, pKa2 and pKa3, right, and that is what we see here 2.2, 6.7 and 11.6. And for arsenous, Again I believe I am missing one value here, but I believe I am missing the pKa 3 value here, but that is fine. The effective range is only these two pKa values. So again we have 9.23 and 12.1, right, and for silicic acid we have the 2 pKa 1 and 2, and we are missing 3 and 4, but that is not required now. For acetic acid, with respect to donating this particular proton, the pKa is 4.76. So we are going to look at a few examples relevant to these particular values, so keep them in mind or at your background, I guess. So the first example is with respect to ammonium, I guess. So background information that I am going to give you is that, let us say this is your soil or subsurface, let us say subsurface, or this is the soil here, okay. So soil in general has a cation exchange capacity, or what does that mean? It means the soil has the ability to hold on to cations now, right. It has the ability to hold on to cations, and I believe I also need to give you the pKa for HNO3 or nitric acid. Looks like that is minus 1.3, right. pKa for nitric acid is minus 1.3. So again we are coming back to our example. Soil has a cation exchange capacity, right, and more or less that means soil can hold on to cations, right. And so let us say if a particular farmer has two options for adding nitrogen to his soil, right. He can either add it in the form of nitrate, right, or in the form of ammonia now. So which one would you choose and why, or which one would you suggest and why, let us say, right. So here the key is again pH. So it is a fertilizer, soil needs nitrogen, right. He can add it in the form of nitrate or ammonium now. So the key is that if you add it in the form of nitrate or NO3 minus, let us say, and as you see the pKa value for HNO3 and NO3 minus is minus 1.3. So our effective soil range, let us say, is around pH 7, and we see that the pH is greater than pKa, right. So what does that mean now? So this is the pKa, and so this is the pH and pKa. So pH is greater than pKa, right. So what does that mean? The deprotonated form, or what is the case here? NO3 minus predominates. So NO3 minus predominates at pH 7. That is something that you can now understand, I guess. But with respect to ammonia, let us say ammonium, NH4 plus can dissociate into NH3 and H plus, right, and that is what we have here. But the pKa value for this particular case seems to be 9.25, the pKa1 value is 9.25. So for this case though, right, pKa is 9.25 and the pH is going to be 7, pH is 7. So here we see that pH which is 7 is less than pKa which is 9.25, right. This is what we see in this graph here. So this is the pH of the soil. So at that particular pH, which form predominates? We see that the protonated form or NH4 plus would predominate, right. So NH4 plus would predominate at pH 7 and NO3 minus will predominate at pH 7. So this is the take home message though. But the issue is that the soil has a cation exchange ability or can hold on to cations now. So it can hold on to NH4 plus but not hold on to NO3 minus. So whenever there is any rain, let us say, what happens now? NO3 minus can be leached away, right, to the ground, but in general to the subsurface, but NH4 plus in general can be held on to by the cation exchange capacity of the soil. So thus the farmer would be better off, what do we say, dosing NH4 plus rather than dosing NO3 minus. So what is the key here again? We looked at pH and pKa, right. So again we will just summarize what we just discussed right now, and the example we were looking at was we also had to have the information for pKa for HNO3 and NO3 minus, and that was I think minus 1.3, and we are trying to see which one would be a better option, NH4 plus or HNO3 or NO3 minus, which one would be better. And we know that the soil exists in solution at around pH 7, not exists in solution, pardon me, the soil pH we are assuming is equal to 7, right. and then we looked at our speciation graphs. This is a speciation, I guess, right, for both the cases. So, one is for ammonium, pKa is 9.25, and we see that at pH 7 most of it stays as HA or NH4 plus. And what does that mean? It is going to it as NH4 plus has a positive charge, right, but we know that at pH 7 HNO3 is not going to predominate, but NO3 minus, because pH is greater than pKa, right. So, we are going to have an anion, but with NH4 plus it is going to stay as a cation, right, and negative charge here, right. So, what does that mean? The soil can hold on to NH4 plus, but not onto NO3 minus, right. So, in general the farmer would be better off applying ammonia rather than nitrate for his source of nitrogen. So, that is what we have just observed, I guess. So, let us move on to the next example here, please. And the next example is, let us say, by ion exchange, right, by ion exchange at, let us say, around pH 7, you are trying to remove arsenic, right, arsenic by ion exchange at around pH 7, let us say. So, in which form would you rather have your arsenic? You know, we have not talked about redox form set, so I believe the oxidation states are different in both these cases. So, would you want it to be in the form of arsenic or arsenous, arsenic acid or arsenous acid? So, here let us say at pH 7, right, at pH 7, if I look at H3ASO4, what is the speciation going to be here? So, let me draw the figure here, right, we never looked at the triprotic acid before. So, it is going to decrease again, and this, so it is going to be H3ASO4 here, H2ASO4 minus, HASO4 2 minus, and so on. We still need to look at the other deprotonated form, but let us limit ourselves to here. And what are the pKa values? They are 2.24 and 6.76, right. So, what does that mean at pH 7, right, which is our key, and where is pH 7? So, somewhere here. So, the species are going to be, or the forms that predominate are going to be HASO4 minus, and more importantly HASO4 2 minus. So, what does it mean? I guess they have a charge, or we have anions predominating, or we have a charge, the negative charge. In general, it is going to be HASO4 2 minus. So, that is what we see here, right. This is pH 7, pH equal to 7. So, what is this graph about? This is for a triprotic acid. I have not drawn the pKa value for the third case, or the pKa 3. I am just limiting myself to 2.24 and 6.76. So, H3ASO4, as it keeps decreasing, H2ASO4 minus keeps increasing, and as that again further decreases, you are now going to have HASO4 2 minus. So, what are the relevant equations? Obviously, H3ASO4, right, would go to H2ASO4 minus plus H plus. This is one relevant reaction relevant to this particular region, right, and the other is the other dissociation, the next dissociation, I guess, dissociating into HASO4 2 minus and H plus, right, and this is what we see here in this particular region, right. So, again we will try to erase this and get back to a better format. So, we see that at pH 7, what were predominating? I guess the HASO4 2 minus and H2ASO4 minus. So, more or less the take home message is we have a negative charge on the relevant species. So, the total arsenic will be present in HASO4 2 minus and H2ASO4 minus. But if I come back to arsenous and I look at that particular figure, so if I draw the diagram here, so obviously this is not to scale, that is the reason if anyone is having an issue. So, I am just going to draw the two pKa values here. So, H3ASO3, what can that H3ASO3 can dissociate into H3 pardon me, H2 AS O2 O3 minus plus H plus, and again H2 AS O3 minus can further dissociate into H AS O3 2 minus, and again another H plus. So that is what we have here, and so the pKa values for that though are 9.23 and 12.1. So here we are only looking at pKa 1 and 2, but for our pH range, which is 7, so that is going to be somewhere here. So as we see, at pH equal to 7, which form predominates now? It is the protonated form, and that is H3 ASO3, I guess, right. So what does this mean now? It means that this has no charge, right. In this oxidation state of arsenic, there is no charge at the usual range of pH 7, yes. So can you use ion exchange to remove a compound with no charge, at least especially with this case at pH 7? No. So in which form should arsenic be present if it wants to be, or if you want to remove it by ion exchange? It needs to be in the oxidized form, and why is that? Only because in the oxidized form you see that it has a negative charge, and only then can it be removed by the ion exchange process. So I guess with that I will end my session for today, and we will continue the other examples in the next lecture session. And I also request that you try to install a software called vMinTeq. So you can Google this, vMinTeq, MINTEQ. So we are going to start discussing the applications. I think it is not of a greater file size, maybe 10 MB or 20 MB at best. You can just Google it, Visual Minteq or vMinTeq. The first search result itself should give you a free download option or download option. So please have this loaded for your next session, I guess. Again, please try to look up Visual Minteq or vMinTeq. It is a software we use to model or model equilibrium, I guess, and we are going to use that throughout the class. So it is a free to use software, or free to download and free to use software. So with that I will end my class for today, and thank you.